Hello, I'm Sean, a PhD student at CSIRO and Australian National University. I will be presenting our paper titled Homography Guided Temporal Fusion for Road Line and Marking Segmentation, a collaborative work involving Data 61, CSIRO, Australian National University, and Sun Yat-Senator University. Firstly, I will introduce the task. The task is pixel-wise classification of road lines and markings. It diverges from lane detection tasks that emphasize identifying drivable area boundaries rather than capturing the actual lane shapes. Our work is motivated by the observations road lines and markings are 1. Frequently occluded in the presence of moving vehicles, shadow, and glare, and 2. Highly structured with low intraclass shape variance and overall high appearance consistency. To tackle these issues, we introduce the homofusion method. Homofusion leverages adjacent video frames to provide complementary cues that enhance accurate classification of partially occluded road lines or markings. Here is an instance shows the effectiveness of homofusion. In the top left subchart, we observe a straight arrow, with its bottom half hidden behind a vehicle in the current frame. In the top right subchart, based solely on the current frame, the straight arrow is mistakenly classified as a right turn in straight arrow, and the dotted line is erroneously identified as a solid line. With the application of homofusion, which draws insights from adjacent video frames to provide supplementary cues, see bottom right subchat, both the straight arrow and solid line are correctly classified. Then, I will introduce our method in details. This is the overview of our proposed method. It consisting of a pair of lightweight encoder and decoder, our proposed homofusion module. Homofusion module employs a pixel-to-pixel attention mechanism. Incorporate information from previous frames by projecting the pixels of the current frame onto the previous frames. We use this homography transform equation to project pixels. In the homography transform equation, road normal vector is unknown. We propose road surface normal estimator module to estimate it. Then, I am going to introduce the data flow. A sequence of frames are encoded into the feature representations. Road surface normal estimator estimates the road surface normal vector based on first-level adjacent features. The estimated normal vector, combined with the camera intrinsic and extrinsic parameters, we establish cross-frame correspondences by homography transformation. Uses transformer mechanism, using current frame as query, previous frame as key and value, we obtain fused representation. Finally, the decoder decodes and upsamples the fused feature to predict the lane mark segmentation. Then, we introduce the details of homofusion. Homofusion module employs a pixel-to-pixel attention mechanism. Incorporate information from previous frames. Here is the fusion equation based on pixel P. PT is the 2D pixel in current frame, PI is the projection in previous frames. Pixel correspondences are established through homography. Fusion weights are computed based on normalized feature similarity. Then, we introduce the details of road surface normal estimator. In the equation of homography transform, we assure camera intrinsics, extrinsic and height of the onboard camera are known. The normal of the road surface can vary due to the unevenness of the road surface, such as uphill or downhill roads, and sloped turns. Therefore, to accurately estimate the road surface normal, we employ the Liebenberg-Marquardt algorithm. The road surface normal estimator engages in an iterative process to refine the estimated normal based on projection errors of on-road pixels from the current frame onto previous frames. We begin by sampling pixels from the current frame that are likely to lie on the road surface within the triangular area situated in front of the vehicle and below the disappearing point. Using the same homography transform, we can get residual of current normal vector. The optimization unfolds in an iterative manner through the following procedure. The optimization of the estimated road surface normal occurs iteratively through the following steps. Calculate point coordinates using homography. Derive point feature from first-level feature map. Calculate residual. Observe error and robust cost. Construct Jacobian and Hessian matrices. Obtain update normal by Koleski decomposition. This instance showcases how the estimated road surface normal affects homofusion. Finally, I will introduce the results. In the quantitative comparison, our approach demonstrates superiority over the existing state-of-the-art methods across both the ApolloScape and ApolloScape Night datasets. Our approach achieves this while employing less than 9% of their parameters. Through a qualitative comparison, it is evident that our approach exhibits higher accuracy and a reduced occurrence of false positive segmentation. Thank you for listening.